Imagine holding a device no larger than your hand, yet powerful enough to challenge everything we thought we understood about computation. This isn't science fiction or a distant prediction. It's a real technological achievement that has forced scientists to rethink the limits of physics. In late 2024, Google's quantum processor, Willow, completed an incredibly complex calculation in less than 5 minutes. According to researchers, solving that same problem with today's most advanced classical supercomputers would require an amount of time so enormous that it stretches far beyond the age of the universe itself. The difference isn't simply a matter of speed. It raises a far deeper question about the nature of computation. As physicists examined the result, they noticed something unsettling. The amount of computational complexity involved seemed far greater than what the tiny processor should realistically be capable of handling on its own. It wasn't merely impressive performance. It hinted that something much more unusual might be taking place beneath the surface. That led to a fascinating question. If the required computational resources appear larger than what could physically exist inside a single chip, or even within the observable universe, then where is all of that computation actually happening? When Willow was announced, most headlines celebrated its incredible speed. But the real story wasn't the stopwatch. The truly remarkable aspect was the scale of the achievement. The comparison wasn't just dramatic, it bordered on incomprehensible. The estimated time required for a traditional computer to solve the same task extends so far beyond ordinary measurements that familiar units lose their meaning. Even if every supercomputer humanity has ever built had been working continuously since the earliest moments of the universe, the calculation still wouldn't be finished. Yet Willow completed it in only a few minutes. This isn't the same as making an existing computer faster. It's closer to discovering an entirely different method of computation. Earlier quantum processors, including Google's Sycamore chip, had already hinted that quantum machines might eventually outperform classical computers on specialized tasks. At the time, many researchers believed conventional systems could eventually narrow the gap through improved algorithms or more powerful hardware. Willow changed that conversation. Instead of demonstrating a modest advantage, it suggested that quantum and classical computers may operate in fundamentally different computational worlds. Traditional computers process information step by step. Every calculation follows a sequence of logical operations, each building on the last. Regardless of how powerful the hardware becomes, the underlying process remains sequential. Quantum computers approach problems from an entirely different perspective. Rather than using ordinary bits that represent either a 0 or a 1, they rely on quantum bits, qubits, which can exist in combinations of multiple states simultaneously. This property, known as superposition, allows a quantum processor to represent many possible solutions at once instead of evaluating them individually. But superposition alone isn't what makes quantum computing extraordinary. The real power emerges when qubits become entangled. Once entangled, their behavior becomes deeply connected, allowing the system to represent an astonishing number of possible configurations. As additional qubits are added, the computational space doesn't grow gradually, it expands at an exponential rate. By the time a processor reaches more than 100 qubits, the number of potential quantum states becomes unimaginably large. In fact, that number exceeds the estimated count of atoms within the observable universe. Pause for a moment and think about what that means. A processor occupying only a tiny amount of physical space appears capable of representing more possible states than there are particles available to physically store them in the known universe. That realization introduces an uncomfortable paradox. Classical computers perform every calculation directly within their hardware. Every operation can be traced to physical circuits and electronic components. But if a quantum computer explores an enormous computational landscape that seems too vast to fit inside its own physical structure, Where is that work actually taking place? That question marks the point where engineering begins to overlap with philosophy. For decades, one interpretation of quantum mechanics has proposed a startling possibility. Known as the many worlds interpretation, it suggests that every quantum event allows multiple outcomes to exist, each unfolding within its own branch of reality. To many people, the idea sounds like pure science fiction. Yet several respected physicists, including pioneers who helped develop quantum computing itself, have argued that this interpretation provides one possible explanation for the strange behavior observed in quantum systems.